Good morning, everybody. My name is Benjamin Jacob Davis. This is for National University's CSC338 Data Structures and Algorithms class. And the topic of choice that I've chosen is the binomial heap. Just as a quick overview for the agenda for this presentation, is I'm going to start out with just a general overview of heaps and then kind of build onto that with a more acute and specific look into binary heaps and then into the binary tree, how binary heaps are associated with binary trees, and then finally the overall topic, which will be binomial heaps, which is what the entire presentation is about. I just wanted to kind of build into that because binomial heaps is actually a specific implementation of binary heaps, which is of course associated with heaps in general. This is just the cover page for the heap section of this presentation. Heaps, the heap concept. Binomial heaps are a specific implementation of heaps, which is why we're covering heaps, covering a more a wider view of heaps in general, that way, just to ensure that you have the base knowledge to understand the more specific and acute view of heaps. To best understand binomial heaps, we will cover heaps as a data structure alone and build our way up to the primary topic. Some applications may require fast access to and removal of the max item in a changing set of items, and that's kind of when heaps become useful for us as programmers or computer scientists. And an example that I'm sure we're all familiar from class is a computer may execute jobs one at a time in a changing set of items. For example, computer executes the pending job having maximum priority. Example, 4 pending jobs have priorities of 20, 12, 90, and 42. The computer would execute the priority of 90, then ascending in order downwards. And then, of course, as new jobs arrive, they will arrive with a priority and be queued as such. And then, yeah, exactly, computer executes the pending job with the highest priority. Maintaining jobs in fully sorted order requires more operations than necessary, since only maximum item is needed. So hence a max heap is a complete binary tree that maintains the simple property that a node's key is greater than or equal to the node's children's keys. And that's, I'm sure it sounds familiar to you because it's exactly what we covered in our textbook when discussing binary trees. But the max heap can be any sort of tree, but is most commonly the binary tree, which is a node's key being greater than or equal to the node's descendants' keys is the basic concept to the max heap binary tree. And the most important piece of information that we can remember from that is that a max heap's root has the maximum key always. And as you see, the visual on the left is just a graphic that can describe that easily, and I'm sure most of you will have no problem with. As you can see, the root key is 98, which is, as we check, is greater than or equal to 50 on the left side of the tree, and then on the right side we see that 98 is greater than or equal to 22. So we know that the properties of this max heap binary tree are true so far. And if we move down on the left side, 50 is greater than or equal to 49, and it is also greater than or equal to 47. And on the right side, we see that the node 22 on the first level is greater than or equal to 14. So we know that this is a binary tree with the max heap property applied. But max heap property isn't the only one. There's actually 2 types of properties that can be associated to heaps and binary trees in general, and that's the maximum, which is what we just discussed with the visual graphic on the left, or the minimum heap, which is almost just the inverse of the max heap property. It's just that the root The root node is the minimum key of the tree, and it is sorted in order downward. The max heap tree maintains a simple property that a node's key is greater than or equal to the node's children's keys, and the min heap maintains the root node key is less than all keys present, and this continues to be recursively true throughout the tree and all subtrees. A max or min heap can be implemented with any tree, but is commonly used as with the binary tree. I think I mentioned that in the slide before. And then the max height of a max heap given n nodes is log n. And common operations for heaps will be the percolate movement of a node in max or min heap, the insert remove function, and the insert and remove have a O log n worst case time complexity. And then common applications of heaps are priority queues, binary heap, binomial heap, and then order statistics. We're going to kind of breeze over a few of those. So binary heaps, this is just sort of going to be a quick overview of the binary heap. It's not the primary focus of this presentation, but I felt like in order to best understand binomial heaps, we needed to at least address binary heaps. Binary heap. Since the binomial heap is an extension of the binary heap, we will spend a couple minutes in review of the binary heap, of course. And you see on the right is just a graphic of a binary heap implementing the max heap property, or the min heap property, excuse me. Let's actually go back really quick. I wanted to say a little bit more about binary heaps, and it's just that before I move on to that binary tree slide, is that the binary heap is a binary tree with specific properties, and it's those two primary properties that make it a binary heap is that it's a complete tree, which, if you remember from our textbook, is that all levels are completely filled except possibly the last level, and the last level has all keys as left as possible. This property of the binary tree, of the binary heap, makes it suitable to be stored in an array. A binary heap, and the second property is the binary heap is either a minimum or a maximum heap, and we've already kind of discussed the differences between a minimum and minimum and maximum binary heap, and it's simply that the key at root must be minimum among all keys present for a binary heap applying the min heap property. The same property must be recursively true for all nodes in the binary tree, and the max heap is, as we discussed, the inverse of the minimum heap. For the binary tree itself, we did cover this in our textbook, but just for a general good understanding, we'll see for the max heap property, we see that the root top node there is 77, and it is the maximum key to this specific tree. And to verify that the property is true throughout the tree, we'll see that 44 is greater than 33 on the left side here, and 44 is greater than 22, so we know that that left subtree is valid. But when we go to the right side, we see that 55, which is the second child of the root node, 55 is not greater than 60, which is the left child of the 55 node, and obviously this is a violation of the max heap property and would need to be addressed if this was a true implementation. And then for the min heap property, it's just more visual displays here to just sort of aid our ability to understand the min heap property. You can see that 10 is the lowest key on this left graphic, and 10 is less than 15, which is less than 40, and n is less than 50, and then 10 is less than 30, which is less than 40 and is less than 100. And you can kind of go through it for yourself here on the right side. The binary heap is a binary tree with specific properties. We kind of addressed that, but to cover it one last time, is that it's a complete tree, which means that all levels are completely filled and the last level does not need to be filled, but all keys are as left as possible, and the heap either applies the maximum or minimum heap implementation. The binary heap is a complete binary tree, most easily represented as an array. And how we represent a binary tree as an array, as we can see over here on the right, is just a helpful graphic that displays a max heap in the array format. That way this really helped me personally, because it gave me that visual aid, because at first I struggled with visualizing the tree format in an array form, so I thought it was a very, very helpful graphic. But the array's form is produced by traversing levels left to right and top to bottom. And you can see that the 0 position on the array is the root node, followed by 58 and 44, which is the children of the root node, and then 55 and 16, which is the left first level's children, 55 and 16. And it just sort of continues that pattern throughout the whole tree, regardless of the size of the tree. So the binomial heap. Binomial heap is a collection of binomial trees. It applies the min heap property or the maximum heap property. The key difference between binary and binomial is just the structure of the tree itself. A binary heap is a single tree, while the binomial heap is actually a collection of trees. Each tree is ordered based on the specific implementation of either the minimum or the maximum heap property. And one of the major benefits of binomial heaps is that it allows for efficient merging of heaps. And we discussed this at the beginning, but the binomial heap is a specific implementation of the heap data structure. And binomial heaps are collections of binomial trees that are linked together, where each tree is an ordered heap. In a binomial heap, there are either 1 or 0 binomial trees of order n. The number of elements a tree is given is depicted by the order of that tree, which we'll get into in this next coming slides. One of the primary applications for binomial heaps is to implement the priority queue, which many of us have heard about. And with that comes the implementation of many types of algorithms, such as the shortest path finding algorithms that we've been learning about throughout this course. And these fast operations make algorithms more efficient. To continue binomial trees, the binomial tree of order 0 is a single node, and then the binomial tree of order n has a root node whose children are roots of binomial trees of orders n-1, n-2, and that kind of continues to a pattern of 0. And I'll cover that a little bit more in depth in the coming slides. The height of the tree is the order of the next node, and an example of that is the 0th order node has a height of 0, and to continue that, a node with order 1 goes to level 1, a node of order 2 goes to level 2, and continued. And there will be a total of 2 to the power of n nodes in a single binomial tree. Here's an image of a collection of binomial trees. The order represents the number of children the root node can have. The 0 node has only a single node, and the order 3 node has 3 children. It's kind of what we discussed in the last slide, and you can see this is just a visual representation of that. all the way to the left is a node. A zero order node has a single node, and then and then it just sort of continues along each tree. A tree with the first order has 2 nodes there, and it just continues on. So a binomial heap with 13 nodes and this particular example is a collection of binomial trees of order 0, 2, and 3. So the tree of order 0 is just a single node 12, while the tree with order 2 is the 10. It has 2 children, which is what that order what that order would require. It has 2 children, 15 and 50, and below 15 is 30. And then for our third binomial tree in this heap is, as you see, the root node being 20, and that 20 has 3 children. Often implemented using doubly linked lists. This seems, from what my research has been able to tell me, is the most common implementation of binomial heaps, which to describe, as I'm sure we're all familiar with doubly linked lists, is that parent nodes have pointers to children and children have pointers to the parent, and that's really the primary requirement that a double linked list has, right? But each node will store the parent pointer, the left and right siblings pointer, the leftmost child pointer, and the number of children and key of that node, which I thought was interesting because it's a lot of information along with the data for each node. And just to continue with that, for a binomial heap with n nodes, I just wanted to reiterate this section, is that the node containing the minimum element is a root of either n0, n1, or continue that pattern. And for binomial heap properties, every binomial tree in a binomial min heap obeys the min heap or maximum heap properties. And we've already kind of discussed what those entail. For binomial heap operations, binomial heaps contain the same classic functions found in our other heap representations, and if you remember from our textbook, those can be kind of generalized to find max, find min, insert, remove, and etc. The normal functions or operations that we would use in conjunction with heaps or even binary trees. But the operation that I thought was most worth noting and kind of discussing was the merge function, which is used to merge 2 pre-existing heaps, which is considered one of the primary benefits of using binomial heaps, is the ability to do this efficiently. And here we'll see an example of that union or merge, which, given 2 binomial heaps, h1 and h2, which you can see in the very first level up at the top, labeled in A, the idea is to merge these 2 heaps together into a single binomial heap. And the first step is to simply merge the 2 heaps in non-decreasing order of degrees, and we'll see that in B that we've simply merged them, but that now it's not necessarily a heap a binomial heap, because the trees are out of order. But after the simple merge, we need to make sure that there is at most 1 binomial tree of any order. To do this, we need to combine binomial trees of the same order. So to do this, we're just going to traverse our list of head nodes here, and we're going to see, do any of our trees have the same order? And in this case, no, none of them do. So we move on. We see that none of them are the same. So we go on to the next idea, which is to simply order the head nodes from smallest to greatest based on the order of the binomial tree. And we can see that we can see the process of that as we move on down. Hey, I just wanted to thank you all for watching my presentation on binomial heaps, and I look forward to your comments.